Recording is on.
So me and Valero will moderate this session. We are both from the University of Brest in France, and we are both members of the yICPMF community. So the yICPMF is a global initiative of early career scientists working to promote education, collaborations, um, and knowledge sharing in the field of predictive microbiology and food modeling. Um, This free open access webinar series is part of our mission to build a strong international community by connecting students, researchers, and professionals with experts in the field. So we're really happy you're joining us today, whether you're here live right now or watching the recording later. Uh, so with this being said, I would like to invite Professor Priscilla Gonzalez Baron, who will moderate the session with us and will give a brief presentation of the ICPMF things.
Good afternoon. Can you all hear me well?
Yes, it's very good.
Yes.
Okay, excellent. Okay, so first of all, good afternoon here in this part of the world, in Europe, and good morning to people that are in America, because I've noticed some people known to me. So first of all, I want to welcome you, all the students that enrolled today to this webinar. First of all, I would like to congratulate Natalia Fernandez and Jan Costa for organizing this series of webinars. I believe the topics are very useful for all the students that are starting and working within the field of predictive modeling. And of course, not only predictive microbiology, but in general predictive modeling in foods. I was lucky to meet some of you in Greece. It was great to meet you and to see also for some of you the work, in which topics you are doing your PhDs. And you have noticed that every time there is more about artificial intelligence or machine learning, LLMs applied to our field. So this is something also that we need to consider, and this is something for Natalia and Jan Costa to consider in the upcoming series of workshops. It will be interesting, like, to add a topic on this, because it's relevant these days. Okay, I think you already know the mission of the ICPMF is to catalyze the development of predictive modeling in foods, and it is primarily done through the organization of these biannual conferences. So this year was in Greek, the next year, it's going to be in Shanghai, in China. And so we have not only the conferences, but we want to make a group to create a strong predictive modeler community that can advance predictive mathematical tools so that everybody can use to have this presence in science and academia. We want to foster the development also and use of mathematical modeling in food science. We have to improve also the food process optimization through the transfer of know-how on predictive modeling along the food chains. So contrarily to what many people think, that the group is only focused on predictive microbiology or risk assessment, is not only. So we aim to cover different domains. And it is also important that as a group we develop educational programs to train food professionals, academia, and scientists in general. So this is all about the ICPMF, but you can find more information on the website that maybe Natalia or Jan can paste the website on the link so that you can access. We'll try to have this updated with news about the group. And okay, that's it. So from my side, so I hope you enjoy the workshop. And I also want to thank Antonio Valero from the University of Córdoba for being here today, taking from his precious time to share his knowledge today. Thank you, Antonio.
Okay, thank you very much, Ursula. And first of all, welcome
So
everyone. Sorry.
just yeah, sorry. I just would like to remind the housekeeping rules before we get started. So,
Okay,
uh, thank you, Professor Ursula Gonzalez Baron, for the introduction of the ICPMF. And just a quick reminder of the housekeeping rules. So, today's session is being recorded, and both the video and the presentation slides will be shared with all registered participants afterward. We will send you a form for the collection of attendance at the end of the lecture. Please fill in the forms for receiving certificates. Please also keep your microphone muted during the talk, and please don't hesitate to type your question anytime in the Q&A or chat box. We'll collect them and present them to the speaker during the session or in the Q&A at the end. Also, feel free to engage and network with us via our Slack community. Natalia already shared the link in the chat, and follow us on LinkedIn for updates on upcoming webinars. Also, if you have any technical issues, please message one of the hosts directly in the chat. So, with the housekeeping rules being said, I would like to introduce you to the speakers of today's session, Professor Antonio Valero. Thank you very much for accepting to do this webinar. Professor Antonio Valero is a full professor of food microbiology and hygiene at the University of Cordoba and the vice chair of the scientific committee of the Spanish Agency for Food Safety and Nutrition. He has currently more than 10 years experience managing projects, training courses, academic teaching, and events in food and related sectors. So his research activity is widely shown as he has published over 70 peer-reviewed papers and book chapters mainly related to application of predictive models in food, microbial risk assessment and management. Um, so today he walk us through a fundamental topic, fundamentals of predictive microbiology, covering ground basic models up to more advanced modeling for application in food science studies. So Professor Antonio Valero, the floor is yours.
okay, thank you very much. First of all, welcome everyone. Good afternoon. Thank you so much for inviting me to take part of this webinar series. I absolutely agree with Ursula that this committee is emerging, and also there are different topics that are being interested by the predictive models community. And to me, it's a pleasure to have all this time with you, of course, and to share this moment and discuss different topics, different things about predictive microbiology. So in this case, we are now entering module number 2, fundamentals of predictive microbiology. I don't know if you can hear me well, or maybe I could adjust my microphone. If someone has any problem, just ask me just to correct my microphone. But I hope that everything will be okay.
We can hear you
So,
well.
okay, thank you so much. So this module is framed as the compass point because our goal is to orient ourselves within the field to understand the basic principles, types of models, and their practical applications in food microbiology. So in this presentation, I will try to explain these three different parts, some introductory terms and also considerations about predictive modeling. Then we will move to the different model types and development. And finally, we will try to explain some model applications. These applications are evolving in the last few years to new computing technologies. And in this case, we will try to approach these applications to food companies for different purposes. So in this case, now, I know that this slide may look overwhelming at the first glance. It's full of equations, But the point is not to dive into every detail. What I'd like you to take away is that predictive microbiology or predictive modeling translates biological behavior into mathematical form, mathematical equations. Each of these equations is simply a different way of capturing how microorganisms grow, survive, or die under certain conditions. So, some of these models are purely empirical, while others embed biological meaning, but all of them share the same aim to transform experimental data into models we can actually use for prediction. So, in this case, this blackboard of equations represents a formal side of predictive microbiology, the toolbox we use to describe microbial growth and inactivation in terms of kinetics and environmental effects. So there is a reason behind these patterns. So there is a transition of different patterns that can happen in nature. Maybe you have heard about this golden ratio. In this case, mathematical modeling is not only about complex formulas. Sometimes nature itself reveals patterns, hidden rules that point in order in microbial behavior. Examples of this are present in this slide, is the golden ratio and fractal geometries. They remind us that mathematics is not just an abstraction, but something deeply embedded in the way biological systems organize themselves. So, while equations give us the tools to model microbial dynamics, natural patterns show us the universality of mathematics in biology. So in this case, the golden ratio is represented by this letter, which is phi, which is equal to 1.618, is a mathematical constant that has fascinated scientists for centuries. So it appears in nature as a principle of balance and optimization, from, in this case, the arrangement of leaves in plants to the spirals of shells. In this case, the fractal patterns are structures that repeat at different scales. So many bacterial and fungal colonies show branching or dendritic growth that reflects fractal geometry, particularly when nutrients are limited or when diffusion dominates. So these fractal structures are not just visually striking, they represent how microorganisms optimize their architecture to maximize access to oxygen and nutrients. So, taken together, golden ratio and fractals remind us that microbial systems, although highly complex, can often be captured by relatively simple mathematical principles. So, predictive modeling builds directly on this basis. By identifying these regularities, we can models that not only describe but also anticipate microbial behavior in foods. So, this is a way on how nature could explain certain could be explained by certain mathematical equations. So, in this case, as Albert Einstein pointed out, in this case, how can it be that mathematics, being after all product of human thought, independent of experience, is so admirably appropriate to the objects of reality? In this case, we will try to explain some patterns that can occur in nature and, of course, in different food matrices. Maybe all of you are very well familiarized with this microbial growth curve, which explains the growth of a microorganism over time. So normally, when when we are trying to fit a mathematical equation, we can construct an equation that are passing through all points with an accuracy that is perfect, as you can see in the slide. But in this case, the biological variability is not representing this unique case. What is happening in reality is that microorganisms can grow differently according environmental conditions, according the the nature of the food matrix, and this initial equation that we fit it to our individual replicate may not be useful if a repetition is made. So, how to describe this microbiological variability? This has been a challenge for food scientists and microbiologists over years, but in this case, it should be understood that the mathematical model should explain the biological behavior of a microorganism in a certain food matrix over a time period. So in this case, you can see that the best fitting is not the same as the best model. Normally, the best fitting could represent an ideal case at certain conditions, but these fittings may not be useful at different conditions. So, to explain biological variability, we should find a model that appropriately describes the data over a certain time period or against different environmental factors. This applies not only to microbiology, but to different factors, different outcomes, for example, modeling different patterns that can occur in nature. There is a biological variability that should be explained by mathematical equations. But the main goal is to find appropriate models that could explain this variability. In this case, we can see that this growth pattern is divided in different phases, in different growth steps. You can see the lag phase, which is the initial adaptation period where the population is not growing, and then the population is growing exponentially. This is related to the exponential phase. And finally, the microbial population is reaching a maximum density population level, which is represented by the stationary phase. So the main goal is to model the description, to model the behavior around all these growth steps. So let's look at this Excel sheet when we are representing the time, the values of the number of colonies in arithmetic units. This is in the second column, and in the third column it is represented the result. So if we try to represent the time against the arithmetic units, you can see that the growth pattern is described in an exponential way. But in microbiology, we can distinguish these three different phases, and we need a transformation to logarithmic units. So this is very important to model microbial growth or microbial inactivation. If we transform these arithmetic units into logarithms, you can obtain the typical growth pattern in a linear way. So in this case, we can estimate microbial parameters that can describe microbial behavior under certain environmental conditions. So in this case, logarithmic transformations are normally used in food microbiology predictive modeling to homogenize the variance between the data. So after all, we can conclude that the model is a set of assumptions and simplifications about what could happen in reality. It is important to note that these mathematical models are a set of assumptions and simplifications, some of which are formulated through mathematical or differential functions, and these models cannot consider all environmental factors that influence on microbial behavior. These models are trying to represent the main effects of factors that are influencing on microbial behavior. So we can define predictive microbiology. This is one formal definition. It's a branch of food microbiology that makes it possible to quantify and predict the responses of a population of microorganisms to different factors that affect it. So this is a definition that was published in the 90s, but it is important to consider that predictive modeling has evolved in the last years to different aims, different goals, and not only microorganisms but other environmental factors are integrated into more complex mathematical equations. But in this case, we will try to focus on the fundamentals, on the roots, to better understand what would happen if considering more complex scenarios. So these complex scenarios are represented in the so-called value chains. You can see in this slide, in this scheme, different factors or variables affecting different layers of the value chain. You can see in the external side all primary or environmental conditions such as climate change, water availability, ecosystems, soil, air, natural elements, societal elements, and core system, sustainability, food security, and so on. All these factors and variables are taking part of the food system and the value chain. So it is very important to understand food systems and to employ these systems thinking. So this is critical to identify the root causes of system failures. So biological systems, as said by Brandt and Roberts in 1995, are extremely complex. So their models must inevitably include simplified idealizations. So one of the first approaches or the first statements was postulated by Monod in 1949 according to microbial growth of bacterial cultures. He said that the growth of bacterial cultures, despite the immense complexity of the phenomenon to which he testifies, generally obeys relatively simple laws, which make it possible to define certain quantitative characteristics of the growth cycle. So in this case, he said that microbial growth can be explained by understanding the main factors that can affect microbial behavior. These factors can be classified or can be modeled into processes, for example, different disinfection techniques, thermal treatment, storage, factors affecting these processes, such as temperature, pH, water activity. All these factors can be included in model equations by estimating different microbial parameters. For example, the growth rate, lag time, inactivation rate, maximum density population, and so on. So these predictive models should be validated before applying in a specific food matrix. In this case, a validated model is a very useful tool for food industries, for stakeholders for decision making to quantify microbial responses in foods. So, in this case, a reductionist approach traditionally adopted to predict these microbial responses in foods. In this case, this is one of the first models that were published. This is in the 1920s. In this case, Meyer in 1922 tried to describe inactivation of Clostridium spores as a function of temperature. So you can see that they estimate a linear equation to predict the decay of the number of spores against treatment time. You can see that this model was one of the first models that were applied at the industry level to predict the inactivation rate of Clostridium botulinum spores in a buffered medium at 100 degrees. But over the 20th century, different studies and evolution of predictive microbiology occurred. In this case, in 1922, with the first death rate models for spore-forming bacteria. In 1949 and 1937, Scott and Monod postulated or estimated the knowledge of temperature effect on the growth rate. In 1964, it was a Torrey scale for estimating the fish shelf life. In 1971, 1973, the first growth probability models for toxin-producing microorganisms were published, and the systematic approaches for growth and inactivation models were adopted in the 80s and also in the 90s by different authors, as you can see. And the new area of predictive microbiology tools appeared in the 90s with the first launch of Combase database. As you can see, this is a very well developed database on predictive microbiology. So from the 90s, this predictive microbiology has evolved, and there are different books that published the main principles of microbial responses in foods. You can see some of the most important books published on predictive modeling with different point of view, and later there are some books published on model applications in the food industry. Predictive microbiology is a very important field, and you can see that in some databases you can find nearly 60,000 results with these keywords. So in this case, there are plenty of studies published at this regard in this field of predictive modeling. So you can note the importance of this field for different applications. We will try to explain some of the most important model types and how these models can be developed. So this would be this second part. There is a traditional classification because different terminologies lead to different purposes. There has been an evolution on the terminology that is used for predictive modeling. The traditional classification stated that models can be classified according to their development into primary, secondary, and tertiary, but there are some other terms that are used to classify models. The first criterion is according to their development. This criterion is according to the purpose, to the final purpose. You can see that models can be classified into growth, inactivation, survival, or probability according to the nature of the equation that is used and maybe the assumptions or hypotheses that are behind this model structure. Models can be empirical or pseudo-mechanistic if they include some biological interpretation in these equations. And also, according to the outcome of these models, they can be deterministic when they estimate a single value, or stochastic when these models are estimated a set of values or a distribution of values. So this is a traditional classification, but in the last few years there are some other terminologies that are not so novel definitions, but it is useful to know the main distinction between, for example, static or dynamic models, which are used according to the different temperature or profiles of different environmental factors. Single cell and population models were on the rise in the late 90s and also in the beginning of this century. Especially single cell models can explain the biological behavior of these individual cells and how these individual populations can be reproduced in certain environments. And according to the mathematical adjustment, these models can be also classified into one-step or two-step modeling. So Each approach, of course, has their own advantages and limitations, but you can see that different terminologies are used when building predictive models, and according to the final goal, to the final purpose, we may choose the most suitable model to be employed. So, before developing a predictive model, of course, we need data, we need quality data. It is very important to have a good set of data because different equations can be fitted, but if data are not of good quality, of course, models at the end will not be good. So first, we can ask ourselves some of these questions, which are very important to know beforehand. For instance, the first question, which is the target microorganism being studied, or which is the target outcome being studied. In this case, it is different to develop a model for microbial spoilage or for a foodborne pathogen or for different purposes, for estimating the shelf life or in this case to demonstrate the compliance of microbiological criteria. So in this case, it is important to know the target microorganism that is being studied. Second, which are the food characteristics? The food matrix is influencing microbial behavior, not only chemical factors, but also the physical structure of the food matrix is influencing microbial growth or microbial survival under certain environments. There are plenty of publications dealing with this aspect, the influence of the food matrix, the physical effect of the matrix on microbial behavior. In this way, it is important to consider that models that are developed in growth culture may not be applied in different foods, in part because of the effect of this food matrix. That's why it's very important to validate these models. What is predicted by the model? We will see how the final goal is, or what the final goal is. So what is predicted by the model? It is predicted the growth, inactivation, survival, probability, of course. This largely depends on the problem's nature and also on the stakeholders' interest. In our case, we found that food companies have different problems and we may adjust the suitable solution, the suitable model to solve this individual problem, this individual case. So in this case, it is very important what is predicted by the model. This is a key question. Are all the factors relevant to the food of interest included in the model for the growth, inactivation, survival of the microorganism? In this way, we may use a model that includes all factors, or at least the main factors that are influencing on microbial behavior. If we estimate, for example, the microbial growth or microbial behavior in an acid food, and we don't have a model considering the effect of pH or the effect of organic acids, this model may be useless for our purpose. So it is important to consider a model that includes the main factors or as many factors as possible to estimate microbial behavior in the specific matrix. What type of data is the model built on? In this case, we can see that models can be developed in absorbance units, in plate counts, so it is important to consider the type of data, the nature of data, to see if there is a need to calibrate this model for different applications. This is a question that is very important for food companies because in some cases they don't apply models in a proper way because they don't know the model domain. So it is important to see which is the model domain. The model domain is understood by the range of factors or the levels of the factors where the model can be applied. So in our case, we could consider a model with a specific domain, for instance, domain in temperature, in pH, water activity, and it is not advisable to make prediction outside this model domain unless the model is validated at these conditions. So for instance, if the model considers a temperature between 5 and 30 degrees, we cannot apply the model outside this range because the model can be biased, can provide biased estimations. That's why it's important to know very well the model domain to correctly apply and interpret the model's outcome. And finally, how can we understand that the model is validated? So, what is the degree of accuracy and precision of the predictions in the food of interest? This is related to models validation. So, in this presentation, I will try to describe the main statistical indices, although there are more in literature, but at least we can see how a predictive model can be validated. We will try to focus on models classification according to their development into primary, secondary, and tertiary. So we can wonder these questions, for instance, for primary models, after 3 hours, what microbial concentration will be reached in a food matrix? This could be a question that can be answered through a primary model. Secondary model at 5 degrees, pH 6, water activity 0.96 in a given food. What is the predicted maximum growth rate? And finally, tertiary models, how one can compare and visualize different model predictions. So, tertiary models are mostly related to different computing or software tools, which will be explained in a different module during this webinar series. But these tertiary models are supported by a previous development of primary and secondary models. In this case, we can find models, in this case published for microbial growth, microbial inactivation with different inactivation patterns, as you can see, or models that can explain microbial transfer. These models are highly important for food industries because these transfer rates can explain microbial transfer from one surface to another. So in this last graphical representation, you can see the transfer rates according to the different slice number in a cooked meat product. So these are other predictive models that are used by food industries to estimate the impact of cross-contamination events. So you can see that the degree of adjustment of the different equations, if you look at the second graph, for example, this fitting may deviate the observations, but you can see that in this case we should find the appropriate equation to model this inactivation or growth patterns. So this is important to have a good set of data and also to have different repetitions, different experiments to apply correctly the most suitable predictive model. So that's why it is important to correctly understand and interpret model parameters. These are the most typical for primary growth models. You can see the initial contamination or in sub-zero, lambdas, the lag phase, time elapsed from the colonization of microorganisms in the medium until they begin to multiply. Growth rate is the increase in microbial concentration per unit of time, and the maximum density population is represented by the symbol Mmax. These microbial parameters can be modeled, and they have an effect in models fitting. So you can see that in this example for Barangi model parameters, you can see that there is a variation in the lambda parameter. The lambda parameter is estimating the lag phase. You can see that the extension of the lag phase can be modeled, as well as the different sigmoidal curves with different number of parameters. As long as we are increasing the number of parameters, of course, we can obtain a more sigmoidal curves. But as I will tell you later, it is not useful to increase so much number of parameters, because we may overfit. We may increase the risk of overfitting, in this case, of these models to our observed data. These are variations in different model parameters, in this case for Barangi equation, variations in M parameter, which affect the stationary phase, or variations in N in parameter, which is affecting the lag phase. So what I'm trying to explain with this slide is that model parameters can affect the shape of this microbial growth curve, and this fitting could affect models estimations. That's why it is very important to follow an appropriate fitting method to obtain a suitable model that can be useful to obtain predictions. This is highly important. Moving to secondary models. Remember the question. Secondary models are trying to provide a relationship between the environmental factors that we are considering against growth or inactivation parameters. These are represented by different graphical illustrations, as you can see in the slide. This is a typical response surface, and you can see the effect of different factors against a specific growth rate of Salmonella. These representations are normally obtained from secondary models. We will try to explain, I will try to explain some examples at the end of this presentation by which these secondary models can be applied to solve a food safety problem. Finally, tertiary models are computing tools, software tools. The most famous is the Combase tool, but there are many others that appeared in the last years, and also these tools have evolved, and I think they will explain in further modules in this webinar series. So I encourage all of you to follow this series to take part of these software tools, which are very, very useful. I'm just explaining or trying to see an example of some of these tools, and at the end of this slide you can see a link by which you can access to the different predictive microbiology tools, predictive microbiology and risk assessment tools. So another classification criterion is according to the purpose. So we can distinguish between growth. In this case, this can be explained by these three microbial parameters. The most important, or one of the most important, is the maximum growth rate, which is the tangent between A and B. So this is the maximum growth rate. This is the slope of the curve, and the lag phase can be calculated in different ways. In some models, lag phase is calculated as an extrapolation of this slope to the x-axis, and also the maximum density population. For inactivation models, we can follow a linear pattern, which is explained by the maximum death rate which is directly proportional, inversely proportional to the d-value. The d-value is the time for the one log reduction, and you can see that the maximum inactivation rate is estimated by the slope of this model. And in these inactivation models, lag phase, the initial lag phase, is understood as the shoulder phase. The shoulder is the initial resistance of the microorganism to the inactivation treatment. So these are basic primary models that can explain microbial behavior over time and are published in the first years of predictive models. So in this case, there are some others. We can see growth probability models. Some representations you can see are very typical. This is a kind of a contour plot where we can distinguish the different probabilities of growth according to the different factors. In this case, this model was published in 2007. This relates time in minutes against the pH, and that zones that are split up into growth or no growth according to different high pressure treatments. And again, microbial transfer models, I explained the importance of these models to estimate the impact of cross-contamination events. So in this slide, you can see a set of equations, and it is not my objective, of course, that you learn by heart all these equations, but in some cases it is good to look at the equation to understand how this model behaves and how this fitting can be made. So this slide represents some of the most important primary and secondary models. Regarding primary models, Gompert's model was widely used to explain microbial behavior over time, microbial growth over time, as well as the trilinear model, logistic model, and Varangi and Roberts model, which are sigmoidal curves. For secondary models, you can see polynomial model, gamma model, cardinal type model, square root model, and a logic model. We will try to dive a little bit in these secondary models, trying to study the advantages and disadvantages of all of them and try to see how and what is predicted by these models. So let's start with the first polynomial model. The polynomial model has been widely used in predictive microbiology. First studies on predictive modeling, normally they use the polynomial models because they are normally very easy to interpret and they easily summarize the information from a data set. These models are very flexible, so any type of environmental factor and their interactions can be included. So polynomial models are normally equations of order 2, but you can find literature order 3, order 4, order 5, and so on. And these models are extremely flexible. Imagine that you have an equation. This is an equation of order 2, but if you find an equation of order 5, imagine that the number of parameters are increasing a lot. This provides a very, very high degree of flexibility. This could be good, could be understood as a good point, but in predictive microbiology, it is not good because this increasing number of microbial parameters may increase the risk of overfitting. Overfitting is when the predictive model is trying to describe not only the microbial behavior, but the experimental error, which is not the main goal, which is not the main intention. So this is a drawback of polynomial models. So polynomial models, they use a significant number of parameters that have no biological interpretation. In this case, for this equation, the there are 9 parameters that are included in this equation. So these models are extremely flexible, which could be good in certain cases, but in most cases are bad because these models don't have biological interpretation and are not used to model microbial behavior but experimental error. So in this case, these models may not appropriately describe microbial growth, but for certain specific datasets or certain specific cases, of course, polynomial models can be a good solution, especially when considering a few number of variables. So let's look at the other secondary models that are used in predictive microbiology. This is the so-called square root or Rutkowski model, which was published by Rutkowski et al. 1982. They found a linear relationship between the square root of the growth rate and temperature in suboptimal conditions. Suboptimal conditions are those conditions that are below the optimal. So in this case, for certain microorganisms, to explain microbial behavior, there is a linear relationship between the square root of a maximum growth rate and suboptimal temperature. This is explained by this equation. This relates the square root of the maximum growth rate with a constant, which is explained by the letter B, and temperature and the minimum temperature. Minimum temperature is a notional value of temperature at which a microorganism is able to grow. So in this case, this relationship is useful to include some model parameters which could have biological interpretation. So this is the case of the temperature minimum temperature of T-min value. This model has been expanded, was expanded later, 1 year later, to extend the whole biokinetic range to include another parameter, which is Tmax, which is the maximum temperature at which microorganism is able to grow. So this is highly useful because with a few number of parameters, we can explain very easily the microbial growth within the whole biokinetic range, as you can see in this graphical representation. This model, this structure, can be expanded with more environmental factors. This is the hypothesis behind the gamma model. Gamma model was published by Swittering et al. In 1992. This is a secondary model that states that the growth of a microorganism depends on the effects that produce inhibition at its optimal growth. So you can see this equation. There is a parameter which is the optimum growth rate, which is the growth rate at optimal conditions of environmental factors, and this optimal growth rate is being multiplied by different inhibitors. These inhibitors are known as gamma factors, gamma inhibitors. So you can see there is a gamma factor for temperature, gamma factor for pH, gamma factor for water activity, and the final outcome of this equation is the observed growth rate. So this is a simple way to consider different factors in the same equation. So the main advantage of this kind of models is that they can expand it, or maybe you can take off different factors and you can keep the same model structure. So they can be used for different validation purposes. Indeed, gamma models and cardinal models are widely used in predictive microbiology because they can be expanded according to the number of factors. One of the drawbacks of these approaches is that we need a good set of data to estimate these parameters, these cardinal parameters. So in this case, we need a set of data, a good set of data to estimate minimum temperature, optimum temperature, the same for pH, the same for water activity, and this applies for cardinal models. Cardinal type models are one of the most important models that are used in predictive microbiology, and they are based on these cardinal values, minimum, optimum, and maximum growth limits. Luckily, in literature, there is plenty of information about cardinal values, and you can estimate or use different cardinal values that are published and trying to validate the model in different foods, or trying to experimentally determine these cardinal values, these cardinal parameters in the lab according to a specific microorganism or strain. This is very useful to explain biological variability, interstrain variability, or interspecies variability, because each microorganism has its own cardinal parameter. So if we are able to determine cardinal parameters for a set of microbial species, we could determine very easily the effect of biological variability of all these strains under certain conditions. There are some studies published on Listeria monocytogenes and also for spore-forming bacteria, Bacillus cereus, especially from the University of Wageningen. And these studies are based on the use of these cardinal approaches, and also different studies from French colleagues that are published on that. So these cardinal models, as you can see, are based on a multiplication of the optimum growth rate by, in this case, a gamma. Gamma is normalized function between 0 and 1 for each environmental factor, temperature, water activity, pH, and so on. So the product combines independent effects on environmental factors on microbial growth. And this is the result. In this case, this is the equation that relates the effect of temperature. You can see that we estimate optimum, minimum, and maximum temperature on the growth rate, and this is the graphical representation of these cardinal models. They are widely used for validation purposes in different food matrices. So we already described some of the most used secondary models, and now we will jump to the model development. Model development, this is just a scheme on how these models can be generated, are based on data. Data could be obtained from literature, from different databases, or from experimental studies that are made in the lab. And these data are used for model fitting, validation, and incorporation in software tools. So let's look at the first part, which is related to the model fitting procedures. Normally, how fitting is being done? We are using a set of values of different microbial parameters or different concentrations at different times against environmental factors. So normally, one of the most basic model fittings is a regression. Regression is trying to provide an equation that relates these environmental factors against microbial parameters, and you can see that there is a range of different software that are used for regression purposes. For linear regression, you can see that Microsoft Excel could be enough for certain cases, but unfortunately, in most cases, nonlinear regression should be used, and for this purpose, you can use a more specialized software, for instance SPSS, or some more sophisticated software such as MATLAB, SAS, R, Python, and so on. For models validation in foods, it is important to understand why is validation needed. So all models have different sources of error. You can see in this slide the different types and severity of errors that can have models. The first error is called primary error. In this case, normally, if you develop the model at ideal conditions in broad culture, normally there will be a biological variability. So these potential differences in microbial concentrations are called primary error. So this comes from raw data. There is another source of error which is called matrix error. So imagine that you validate or develop a model in sterilized food, for instance UHT milk, and there is a matrix error. As I told you before, the food matrix has a different effect, has an effect on microbial behavior. So in this case, matrix error is another source of error. So, and the final error is attributed to microbial differences error. So if we inoculate, if we spike food that is not sterilized, normally the background microbiota that is present in the food could lead to a higher difference in the total error. So this error is translated into variability, and this is very important to be considered when validating a model in a specific food. If this variability is not appropriately described, this model may not be applied in all conditions. So the final purpose is not accomplished. That's why validation is very important. It is important to consider the scenario, the potential conditions or deviations in the product and or in the factors, for example, storage conditions, distribution, consumption patterns, and so on. And these models should appropriately describe all these variability sources. So, from the classical predictive microbiology point of view, there are two main statistical indices that are very well known, which are called bias factor and accuracy factor. Both indices were published by Ross in 1996. In this case, these statistical indices are relating predictions versus observations. So in this case, you can see that the formula is almost the same for both indices, but the main difference is that accuracy factor is considering the absolute value of the logarithmic relationship between the predictions and observations. So in these equations, you can see that y is the response variable, n is the number of observations. For the bias factor, if it is higher than 1, the model overestimates the observation, if we are talking about the growth rates. If this is lower than 1, the model underestimates the observation. And if if the bias factor is equal to 1, there could be an absence of bias. So this means a perfect concordance, or there is bias caused by over and underestimation of observations. So positive and negative signs are cancelled. This is a source of error, but bias factor can be 1. That's why accuracy factor exists. because accuracy factor means that if this is equal to 1, there is a perfect concordance between predictions and observations. And if this accuracy factor is different from 1, normally higher than 1, predictions and observations are biased. So in this case, both indices can properly describe if a certain predictive model is or not validated. So this is just a very simple example considering growth rates. You can see the equivalence line between estimated and observed growth rates. This equivalence line is representing a perfect match. So when observed growth rates equal to the estimated ones, and if you can see bias factor in this case and accuracy factor are equal to 1. This is the perfect case. Unfortunately, this is not the real case. So in reality, what is happening is that we can count on different biological variability, and you can see that in this example, the observed growth rate is higher. In this case, the estimated rate is higher than the observed growth rate. So this is the case when the bias factor is higher than 1, when the estimations are higher than observations. Accuracy factor is higher than 1 as well. So this is a fail-safe model. So a fail-safe model is a conservative model when predictions are higher than observations. Of course, if we would fail, we could prefer to fail in a safe way than in a dangerous zone. But in this case, if we consider a fail-safe model, if this model is too fail-safe, this model can be far away from reality. So this is not interesting as well. So it is important to not consider a too fail-safe model. This is the opposite case. This is a failed dangerous model when bias factor is lower than 1, but accuracy factor, as it takes the absolute value, is higher than 1. This is a failed dangerous model when predictions are lower than observations. This is happening in some cases, in some instances, when more or less the same proportion of data are below and above the equivalence line. In this case, bias factor would be equal to 1, but negative and positive signs are cancelled. That's why there is a need of estimating the accuracy factor, which is higher than 1. So this is the case when biological variability exists. So after talking about, sorry, yeah.
Yeah, sorry to interrupt. Just to
Yeah.
suggest 5 minutes break if you would like to
Oh,
before
okay.
we go.
Okay, okay. That's fine. That's fine. Thank you.
Okay.
Thank you.
Comment dire? So we will have to come back at 5:15, please.
Okay, that's fine. Thank you.
Thank you. ça, moi, c'est so if Professor Valero is here again, we can continue this session if it's okay for you.
Okay, that's fine.
Yeah.
Okay. Okay, can you see the presentation?
No.
No?
No.
Yeah.
Let me see. Okay. Okay. Now?
Yes.
Yes. Now it's
Okay. Okay, good. So let's move to the last point of the presentation, which is related to the different model applications, especially oriented to food industries. So there is a set of different applications of predictive models. We described the different model types, development, but now how all these models can be translated to food companies, or how stakeholders can use information that is provided by predictive models. In this case, you can see five different applications. There are some more, but of course, due to the time restrictions, I cannot extend so much. So I will try to give some examples on HACCP, establishment of microbial shelf life, QMRA, microbial risk assessment, design and formulation of products and processes, and compliance of microbiological criteria. So for the first point, HACCP, predictive models can be applied at all steps in the HACCP process. So the most important is to establish critical limits. So they are used to demonstrate to food authorities that critical limit is appropriately set in a certain process. So a critical limit is a criterion that differentiates the acceptability or unacceptability of a process at a given stage. So you can find different models for different purposes, considering the range of environmental factors. So models that can be used by food companies can include, for instance, the effect of organic acids and pH. This model is relating the death rate against the pH, okay, and also organic acid concentration. And also you can find models to estimate the growth of the microorganisms against the temperature and water activity, and also models that can estimate the effect of nitrate concentration in meat products. So you can find equations that are used for that purpose, storage conditions, models that can estimate the effect of storage, ionizing radiations, the effect of atmosphere as well, or the effect of the high pressure processing on microbial inactivation. So, as well as disinfection treatments in vegetables. So in this case, these models can be used directly by food industries if they are validated in the specific matrices. So, to establish microbial shelf life, predictive models are highly important. I would like to remark that this is a very important demand of food companies, establishment of microbial shelf life, because in most cases they don't know very well how this shelf life can be set, can be established, not only from a microbiological point of view, but for a sensorial or physicochemical point of view. This is just a very simple example to estimate the microbial shelf life in a fresh juice. This is based in a prediction of the maximum microbial load that can be appropriate to estimate if this food can be accepted or rejected from a specific organoleptic characteristics, or there are some more sophisticated applications. This is an application of predictive models to estimate the water content distribution in pairs at time zero and future predictions assuming storage at 20 degrees and a range of relative humidity between 30% and 80%. So you can see that water content is being lost as long as the fruit is losing water over time. So these models are very useful to estimate the loss of water over time, and this is related to spoilage of the product, to the acceptability of the product. So these models are based on dynamic predictions over time. So, for quantitative microbial risks assessments, predictive models can be integrated, especially in the exposure assessment phase. So, you can see that this QMRA is trying to estimate the risk according to specific hazards and food matrices. And these QMRA are based on different data sources, for example, microbial concentration, prevalence, processing factors, dose response models that are based on the infective doses, virulence, and also different population sectors, high and low risk population sectors, consumption patterns, or hygienic practices in domestic environments, cleaning and disinfection, culinary treatments, storage conditions, and so on. So, in this exposure assessment phase, predictive models can estimate the pathway, the microbial behavior during the whole food chain to estimate the final concentration in the product before consumption. This is highly useful to estimate the final risk. These models can be integrated into the distribution chain. This is an example on how these models can be integrated in different IoT devices, including time and temperature data, together with some other metadata sources for product, logistic events, temperature, and this is a good way to describe the traceability of the product during the supply chain. And of course, this is highly useful to estimate the shelf life as well, the dynamic shelf life. Dynamic shelf life is understood as the shelf life being influenced by the different dynamic conditions, for example, temperature fluctuations during transport or different fluctuations in water activity or pH or some other factors. So these are more complex model, more complex approaches, but can provide a real-time estimation of the shelf life at certain conditions. So another application is for the design and formulation of products and processes. So uh, different companies, international companies such as Unilever, they have their own decision making or expert system uh, procedures or software. So in this case, you can modulate the effect of different factors on microbial spoilage or microbial safety of different food products. This is integrated into the elaboration process, and with the help, with the aid of models, one can estimate the effect on microbial growth or inactivation, the effect of different processes, novel technologies, changes in formulations, and so on. Some applications, for instance, evaluation of the consequences of changes in formulation, process changes, areas of interest for product and process development and innovation, etc. And just the last application, but it's very important, is the compliance of microbiological criteria. I would like to describe, to explain an example that has arrived to the Spanish Food Safety and Nutrition Agency in the last few years. You can see that a report was published on the conservation storage conditions of hard fruits in retail establishments. So, in this case, the problem starts with the regulation 852 establishes that foods which cannot be safely stored at ambient temperature must be kept under a cold chain. So limited periods without temperature control will be permitted. So this is the statement that companies could take advantage of. And the question was to assess the feasibility of maintaining half fruits of big volume, for instance, melon, watermelon, pineapple, papaya at room temperature in retail establishments for a limited time, and subsequently storing them at the end of the day in refrigerated chambers, also specifying any additional considerations that may be required. So the main goal of food companies and also logistic companies and supermarkets was to leave these half fruits at room temperature for a limited time period in order to better control the volume of these pieces in the cameras, because they had some problems with the storage of these large volume fruits, because they occupy space in the camera, and also for small establishments it was a problem. So this this question has arrived to the agency. So how to solve this problem? So in this case, we looked at the main microbial hazards, in this case Salmonella, Listeria, and E. coli, VTEC, and also enteric viruses. And we consider factors such as temperature, pH, water activity, sugar concentration, fruit ripeness, contamination source, and so on, which could describe in an appropriate way the microbial behavior in that matrices. And you can see that first a revision of available predictive models was done. You can see in the slide some of them validated for different fruits, melon, watermelon fruits, papaya, pineapple as well. And we implemented these models, and we estimated the predictions on the decreases of in concentrations of Salmonella and Listeria, as you can see, against temperature and time conditions. So in this case, we defined different zones, different safe and dangerous zone, where these log increases were low or high. So in this case, we concluded that cut melon, watermelon, papaya, and pineapple may be kept at room temperature at less than 25 for up to 3 hours in well-ventilated shaded conditions, provided that they are subsequently stored under refrigeration. For pineapple, we concluded that because of the low pH, these conditions may require re-evaluation pending further representative studies. So this requirement was translated to legislation. So in this case, we tried to solve the problem of these logistic companies. Some other uses of models in regulatory science have been applied. So You can see a publication of Messens et al. In 2023 from EFSA. There are different approaches to use models, for instance, to set shelf life marking dates. You can see that there is an approach to estimate the shelf life based on the use of predictive models to consider different variability and reasonably foreseeable conditions. And in the second example, models can be also used to estimate public and animal health risk in case of a delayed post-mortem inspection in ungulates. So the effect of the delayed post-mortem inspection have been modeled, has been modeled in this case using different predictive models. So this can be also translated to the frame of the regulatory science. Of course, all these models or all these approaches are not optimal. So there is a set of limitations, uncertainties in the predictive microbiology field. You can see some of them, and it is very important to set the assumptions and limitations of these models because they help to understand how these models can be applied and also to improve these models' predictions. So, some limitations are related, for example, to the complexity of microbial response, to the combination of factors. So, as long as we are adding more factors, microbial response is more complex to be modeled. The occurrence of sublettal damage and metabolic stress, so the effect on the physiological state of the microorganism, is a challenge to be modeled. The biological variability, as I told you in this presentation, variability of intrinsic, extrinsic, and processing related ecological factors. So, for instance, variability between batches, variability between production conditions, between uh, changes in processing, and, and also between food companies. These sources of variability normally are complex, and models normally have limitations to cover all potential scenarios in food industries. And finally, imprecision and insufficient accuracy of analytical techniques. This is related, for example, to the microbiological methods for microbial enumeration or physicochemical methods for food characterization and ecological factors. These limitations should be considered in these coming years with the evolution of novel computing technologies and also data processing, the different approaches related to the machine learning, AI, and also automation technologies will help to reduce these limitations and to expand the use of predictive models to wider purposes. These are future challenges. For instance, the use of AI and big data to enhance models, to improve models. This is highly important, but it is also important how to use these technologies and how to transmit this knowledge to food companies, how food companies can benefit from this knowledge, and how to preserve data confidentiality. This is also highly important. Shift to dynamic real-world conditions, not only considering the food, but out of the box. So considering more factors around the food, around the environment, and also to cover a wider perspective on the use of predictive models. Inclusion of microbial ecology, omics data, which is also a field very important in the coming years, the inclusion of omics data in new predictive models, trying to estimate the impact of genotypic features of microorganisms in the final response in foods. stronger focus on uncertainty and variability, there is a need to estimate in a better way and interpret the different uncertainty and variability sources, links to consumer behavior and risk assessment. It is important to consider consumers' perspective, consumers' patterns, consumer habits in different countries, because there is a high globalization, international trade, so predictive models can also include the effect of this globalization, integration of models with IoT or sensor technologies to provide real-time responses in certain situations, expansion to spoilage, emerging hazards and antimicrobial resistance. This is related, for instance, to the climate change. There is a new or emerging hazards that may arise, so predictive models can be adapted to these new hazards. And finally, the development of dedicated tools for industry decision support and sustainability. So this is a field that is very important, sustainability, because these models should be oriented to minimize food waste. So these are future challenges that are being addressed in the last predictive modeling conference. I think most of the participants touch all these aspects, but of course there is a high need of developing more sophisticated models in the future, and there is a reason behind all this predictive modeling community to address all these challenges to provide safe and secure foods to human population. Just before finalizing my presentation, I'd like to present my research group. This is called Hybrid Group. We are located in Cordoba, in Andalusia, in southern Spain, and this is a food quality and hygiene safety group. We belong to a competitive unit which is called ENSOEM, which is studying the zoonosis and emerging diseases in collaboration with some other departments of animal health, especially anatomy, reproduction health, and so on. And you can find the link of our website in this slide. So this is just the end of my presentation. So I'd like to thank you for your attention. Thank you for your patience as well. And of course, I will be pleased to answer your questions. So thank you very much.
Thank you so much, Professor Valero. So we are really grateful that you take the time to share your knowledge and experience with us. I think that for all of us, it was very clear, and we learned a lot about predictive microbiology. Before we move to the questions, let me just give you a quick reminder of two things that Kautar already mentioned at the beginning. First, so this session is being recorded, so you'll get access to the video and slides afterward. And second, at the end, we'll share an attendance form in the chat. So please don't forget to fill it in if you want to receive your certificate. All right, so we can move to the question now. I think that we have already collected some questions in the Q&A. So I will start. So I have a question on what types of microbiological data are predictive models typically built?
What type of microbiological data? Yes, in this case, some models are based on indirect observations, for instance, absorbance, flow cytometry, but this is not the ideal case. So models normally, the traditional models are published based on plate count data, of course, but it is good to understand how this data have been obtained, okay, because it is important to note that there is a source of experimental error that may be considered, and it is useful to look into different publications, because In many times, data can be fitted without studying appropriately the nature of this data. So it is very useful to study in depth the data set, the nature of the data, and also trying to um, understand the sense of this data and if these observations can appropriately describe a behavior in food, in, in a typical food. Otherwise, predictive models cannot work properly. So I think it is important before modeling fitting to study these observations. But normally, plate count data are the most reliable for the traditional approach, you know.
Okay, thank you. I have another question. So, um, okay, the accuracy and bias factor is normally used for kinetic parameters, which will be the statistical indexes for model validation in case of having data like log reduction data and
Mm.
not the kinetic parameter.
Hmm. Yes, some other statistical indices, maybe I don't know if they have been explained in module one, but normally the root mean square error is widely used. Mean square error, which explains the difference between predictions and observations, and some other statistical indices are, for example, the acceptable simulation zone, which is used by different authors. This is normally appropriate for dynamic data, which explains the proportion of data below or above a certain limit. So in this case, these indices can be used in case of dynamic data. Yeah, that there are some more, but of course, more appropriate for nonlinear regression for comparison between different model equations. But of course, these are more complex. Mm.
Okay, thank you. So you talk a lot about bacterial growth and inactivation, but in the case of spore-forming bacteria, the life cycle is more complex with sporulation and germination
Mm.
steps.
Mm.
Are there models that can describe these physiological states? Sorry, and are there dynamics models that also take into account changing in the environmental conditions?
For spore-forming bacteria, I understand. Yes, there are models that can explain germination of spore and growth, and also for molds. Okay, this is important for molds, for germination and growth. There are not so many models as, for example, bacterial cells, but of course, there are some models for Bacillus cereus, Clostridium perfringens, Clostridium botulinum mainly, and for molds, there are some studies on germination of spores. So these models can be applied, for instance, to explain, to describe a cooling process. Imagine that the thermal treatment is not destroying the spore bacteria population. So when performing a cooling, these spores can germinate. So these germination models can be applied in that way. Also for toxin producing microorganisms, there are models that can explain the amount of toxin that is produced over a certain time period. But you may look into different publications at this regard. So the main challenge, at least from our perspective, when a food industry is demanding a problem, this is requesting our help, is trying to study very well the problem, the nature of the problem, try to look at the most appropriate studies that can answer this question. So this, of course, needs time, needs dialogue with the company, and also uh, trying to find the most appropriate solution. This is not so straightforward, but from my point of view, this is very nice from our job. So
Okay, and for the sporulation stage, Because I know that the environmental parameters can affect the property of the spore. So we have a few models on that, or
not so many. There are more models for germination than for sporulation. Okay, because this experimental data are not so easy to be obtained. So, in this case, if you perform an experiment to measure microbial concentration of vegetative cells and measure spore, you may try to obtain the dynamic point at which these vegetative cells are transforming into spores. This is not so easy to model, but there are some empirical approaches that can be used at this regard.
okay. So single cell models can assume a bacterial colony to be composed of clones from a single cell. What are the main differences between single cell and the population models?
Especially the physiological states and the lag phase. So single cells may have a very different behavior than population models. Population models may not be applied in all cases because don't forget that in reality, contamination is happening at very low levels. So when we apply a population model, maybe the result is an overestimation of this microbial growth. So that's why individual cells models are very useful to estimate microbial behavior at very low population levels, but also they are very useful at the frontiers at the frontiers of knowledge. So it is useful to understand the mechanisms by which bacteria are being divided. So these models can be used from a scientific point of view. They are not so easily translated into a food context, but they need to be considered because the microbial behavior is completely different.
Okay, thank you. What is Dr. Valero's view on the acceptable prediction zone in model comparison? It is an appropriate tool in selecting a better fitting model aside individual model parameters.
Mhm. Yes, to compare different equations, you mean?
Yeah.
Yeah, well, the acceptable prediction zone is just an estimation of the proportion of data above and below the microbial observation. So in this case, this is highly useful to compare between different models, but there are some other indices. For example, the yICPMF information criterion. This is a statistical index that that depends on the number of parameters. So this is very helpful to compare between different equations. And this is specifically used to compare different models. But yeah, of course, you may know which index can be used in a certain specific case. So to compare between model equations, of course, AIC is one of the most appropriate, or the Bayesian information criterion, which is another one. But acceptable prediction zone can be useful as a rough estimation of models predictions and comparison to a model observation.
Okay.
Yeah.
Do not hesitate to put your question in the chat in the Q&A documents. Predictive models are often applied to very different food matrices. Food matrices are often less or more complex. For example, milk compared to a plant-based drink. How can we adapt these existing models to every new product?
Yeah, I see a question in the chat about a software tool to estimate the acceptable prediction zone. just to answer this question, the software tool can be, if you fit a model in R, for example, or different software package, this index can be obtained easily. So there are different software. And regarding the food matrix, as you asked, yes, of course, you need to know very well the food matrix. So a plant-based, and this was discussed in the last conference in Athens. Plant-based matrices may be totally different from animal-based. So in this case, not only the composition, but interaction between ingredients are also different. So in this case, it is very useful to know the structure of the food, the physical parameters, for example, texture, viscosity, that could affect microbial behavior. Because normally when you validate a model that is built in milk, for example, on a plant-based beverage, so the result may be completely different, because that plant-based milk or plant-based beverage could be different, could differ not only in ingredients but interaction between these ingredients. So you may validate models in the specific food matrix. So these models, of course, can be expanded to similar food matrices, but of course, considering the assumptions behind these models and the factors that are included in these models. So this is very important. And if this is a factor that may influence on microbial behavior, this factor should be included in model equations. If there are no data published at this regard, this data can be obtained from different experimental studies. So this is, I think, in my opinion, the best approach. Okay.
Okay, so we have to validate in any case after.
Yeah, at least to retrieve data from literature, from different databases, to see what is published first, just to not duplicate experiments, which is normally happening in some cases. But of course, if there is not any data, I think it is good to obtain experimental data, because these estimations can be biased. Imagine if you think as a stakeholder, as a food in a food industrial company. So if this model can be used for food safety purpose, I think this should be well oriented to this specific matrix or set of food matrices. Okay.
Okay, I see. Maybe we have a more general question. Which are the limitations and challenges for food business operators to apply microbiological predictive modeling?
Yeah, especially the main limitation is time and resources. So normally, at least in Spain, I don't know, in other countries may have similar problems. They have limited human resources, and also the time that a food company can dedicate to these predictive modeling tools is very limited. So normally they forget very easily how to interpret correctly these models. So from our experience, they need advice, they need consultancy service about how to use correctly these models, these tools. But this is true that in the last years, food companies are receiving better this advice on the use of predictive model and predictive model tools, because they are being aware on the importance of these tools to demonstrate the food safety against the authorities. And we receive different demands from food companies. But still, there is a lack of time, lack of resources, and maybe lack of knowledge, because even food inspectors, which are in charge, who are in charge of the official control, they lack of knowledge about all these tools, or they don't use these tools in a good way. So they need advice as well. So it is important to progress in that area, just to translate all this knowledge to the reality.
In the case of studies of shelf life of fresh cheese, which model of predictive microbiology recommends us to use, and which microorganism considered as targets to use it?
For fresh cheese is maybe a growth model because normally this matrix is supporting microbial growth. The target microorganism could be, for instance, Listeria, E. coli, maybe Salmonella in a lesser extent, but Staphylococcus aureus could be target microorganism as well. But this depends on the specific problem. So in this case, for fresh cheese, at least for Listeria, there are plenty of studies that are published. So in this case, this is one of the target microorganism. Yeah, but Listeria, E. coli, Staphylococcus aureus. Yeah, these are more or less some of
So
the targets.
a lot of pathogenic bacteria.
Yeah, 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 but especially microbiological criteria are oriented to Listeria. So most models are published for Listeria. But yeah, we have had some outbreaks of VTEC in this matrix. So even for Salmonella as well. So Salmonella is on the rise. So at least we cannot forget all these pathogens because outbreaks are still happening.
Okay. Are the predictive models on mold growth reaching the point of reliability as those available for the public regarding bacteria?
The models that estimate the growth of molds, yes, they are important. And also in this case, spoilage that are caused by molds are the main responsible of the food waste. So in this case, these models should be better considered in the predictive microbiology field. They are used, and there are different research groups that are working very well, very tough on this in this area. For instance, Jan is, I think, is working on that very hard, and these models are more complex because they should consider spore forming and also toxin production. But mycotoxins is an emerging problem because of the climate change. So these models will be needed in the next future, or nowadays, even nowadays, because molds, spoilage, or the emerging species of molds in foods is very important, and unfortunately, there will be more outbreaks that will be caused by toxin producing molds. So, in my opinion, they should be considered. Mm.
Okay. Maybe a last question. So when we have inactivation data, so the p-value, from non-linear models, how to correlate this data to calculate the z-value? And it is correct to use the linearization for this?
Yes, the nonlinear models don't consider a linear pattern for inactivation. So in this case, a way to estimate the d-value is trying to consider the linear part of the equation. But of course, the applicability of these set values are have to be applied to the linear part, linear inactivation. So in this case, it's difficult to estimate, to correlate these d values when the behavior is nonlinear, but a way to estimate this parameter is to take the linear part of the curve and try to correlate these d values with the set values. But of course, don't forget that this should be applied to the linear part, because the nonlinear part cannot be explained by this microbial curve.
Okay, thank you.
Yeah, there are there are different software. I recommend Bioinactivation. Is a very good software to estimate all these values for nonlinear patterns of inactivation data.
Okay, thank you. So before you leave, it will be really nice to turn on the cameras for the other firmaments if you would like to, so we can take a quick group picture to share it
sure.
on our social media.
Yeah.
Okay, so I'll let you put your camera. Do not hesitate to smile. Not more cameras. Okay. Okay. 1, 2, 3. Sorry. I think it's good. So thank you so much, Dr. Valero. I think that on behalf of the yICPMF team, thanks a lot for this inspiring talk. Sorry, and of course, thanks to all of you for joining this session today. We hope to see you at the next webinar. I don't have the date for the next. It's
the 8th October.
Okay, so the 8th October. Until then, take care and see you soon. Thank you.
Okay. Thank you very much and congratulations. Okay. Thank you. Bye bye.
Thank you. Bye.
Bye.
Thank you.
Thank you. Bye bye. Bye.
T'as la photo?